the lecture. So I have started my recording. So today we will begin the BJT for part 3, AC analysis. Okay. For me, DC analysis is quite straightforward. For the DC analysis, for the AC analysis, they involve a lot of derivation as well as calculation. Okay, you need to understand in detail in order to do the analysis. Okay. All right, so this is the outline, okay, for the lecture today. AC analysis involve the mid-frequency analysis, okay, using hybrid pi model for common emitter, common conductor, and common base configuration. Okay, so this is just a recall. Okay, we have done this, okay, but I need to recall this before I can introduce to you the AC analysis part. Okay, so for the basic voltage amplifier, so I think all of you has familiar and still remember, okay, for the voltage amplifier model. So you will have to do the calculation or analysis the AVOC, AV, AI, Z in and Z out. So this one is actually the voltage gain. Okay, so this is the voltage gain open circuit. So this is the voltage gain, okay, closed circuit, and this is the current gain and input and output impedance. Okay. Okay, so this is how it looks like. Okay, so this is from the previous lecture, but I put it here so that we can do some recall of it. Okay, so AV, which is the voltage gain, okay, is equal to the V out over V in. Okay, if you want to get your V out, then you have to multiply AV times V in. All right, so this is the output circuit of the amplifier, where this is actually the common amplifier model. Okay, we will be using this type of common model in the AC analysis. All right, so AVOC V in, Z out, and V out is equal to the AVOC V in input equal to the output. Okay, can you give me 5 minutes? Sorry. Sorry, I'm back. All right. Sorry, because someone came in just now. Okay. All right. Okay. Can you hear me? Sorry, student. Can you hear me?
Yes, can.
Okay, great. Thank you. Okay, so you will have to do the analysis for this. Okay, the AVOC V in is equal to V out. Okay, and then this is the what we have done lah in the last class. Okay, so we have input load. Okay, so you have to find V out and V in. AVS. Okay, AVS is equal to the AV V in over VS, okay, where you don't have to memorize this. AVS equal to the V out over V in over VS. So it's like you cancel out the V in, and V in over VS is actually the analysis at the input load, okay, at the input load, okay, this one. All right, so let's move forward. Okay, so I put it here, your own you don't have to go to the previous lecture slide. Okay, I put it together here. Okay, all right. So the BJT transistor modeling. So model is equivalent circuit that represent the AC characteristic of the transistor, and a model uses circuit implement that approximate the behavior of the transistor. Okay, there are two types of models, okay, for the AC analysis, RE model and hybrid pi model. So in this syllabus, we will be using the hybrid pi model. Okay, so what is hybrid pi model? So hybrid pi model is mostly used and very useful for the analysis of high frequency transistor application. So at lower frequency, the hybrid pi model closely approximate the RE parameter and can be replaced by them. Okay, so how is it? Let's take a look. All right. So these are the procedures, okay, to solve the analysis. Okay. So basically, you will perform the DC analysis to find the Q point. So this one, we have done this number one step in the previous lecture. Okay, and then determine the small signal device parameter. So what are the parameter here? These are the parameter which is transconductance and also the internal resistance. Okay, so you will be using the DC values that you got here, okay, in this AC analysis. Okay, and then third step is to draw the AC equivalent circuit. And finally, you will have to find all this. So basically in BJT, it's like continuation analysis from the DC analysis to the AC analysis. So that's why you need to understand all from DC analysis to the AC analysis. Okay, this is very important. Why? Because you will be using the current, the collector current from the DC analysis here in order to find the small signal parameter. Okay. If these are wrong, okay, all these will be wrong. All right. So these are the small signal parameters. So for the hybrid pi model, when you have your BJT, so you have this is your BJT transistor. So you have like this one, the collector. So this is the symbol. Okay, so it's like in AC analysis, you convert this symbol. Okay, you convert this symbol into this one. So this one, we call it as a hybrid pi model. Okay, so you convert this, okay, so with the same node, okay, where you have base, collector, and emitter. So this is fixed, okay, this hybrid pi model is fixed with the current source GMV pi and also the R pi and V pi. So this is fixed, okay, in DC analysis, so you have here is VBE, okay? But in AC analysis, you have V pi, okay, from base to emitter, as well as you have R pi. And then at the output means at the collector, you have GM V pi current source and R naught, okay? So why is the DC analysis is important? Because you will need to find the small signal parameter. So this is the small signal parameter. Okay, so which includes GM, which is the transconductance. All right. Okay, this one is equal to the IC over VT. Where did you get the IC? Is from the DC analysis that you have performed in the DC circuit. All right, so you will be using that IC values inside this AC analysis to find GM. Okay, and then how you find R pi? Of course, beta over GM. Okay, when you have wrong IC, means you're gonna have wrong GM and you're gonna have wrong R pi. Okay, and then next is you will have to find the R naught. Okay, since this is in the circuit. Okay, in the circuit you will need to find the R naught. So R naught is given by VA over IC. So VA is fixed, which is equals to the 26 millivolt. Okay, so this is sorry, VA is given. Okay, usually 200 volt or larger volt. Okay, usually you will get your VA value. Okay, VT is equal to 26 millivolt. Okay, so all this, okay, you will need to remember lah, all these small signal parameter equation. Okay, let's take a look on the first type. Okay, if you still remember common emitter fixed bias, okay, this one, the input is at base to emitter, the output is at collector to emitter. So you have RB as well as RC and the VCC, which is the power supply that you have. Okay, for the fixed bias, of course, you don't have the RE at the emitter. So this is how it looks like. Okay, so in the previous chapter, in the previous part of BJT, okay, if you want to solve the current, the DC current, which is the IB and IC, you would have to do the open circuit of the capacitor. Means you ignore all the capacitor during the DC load, during the DC analysis. Okay, but what happened in the what happened here? Okay, what happened for the AC analysis? Okay, what happened? So this is the first step. Okay, the DC load line will be, the voltage source will be grounded. Okay, and then all capacitor will be shorted. All right, and then you will have to simplify your circuit. Okay, let's take a look how we draw it. Okay, so I have to end this and make another slide. All right, can I hope everyone can see. Okay. Capacitor. Okay, you short all the capacitor. Okay, short all the capacitor. Okay, and then the voltage is grounded. So VCC is grounded. Okay, like that. Okay. Okay, first step is to draw your hybrid pi model. Okay, what is your hybrid pi model? Look at the circuit here. Here. So this is your hybrid pi model. Okay, from base, okay, to emitter, you have R pi. From collector to emitter, you have GMV pi and R naught. All right. So you draw that first. So you have your R pi. So this is AC equivalent circuit. Okay. So at base, you have here your R pi. All right. And then this is your emitter. All right. So at emitter, you have GMV pi and R naught. Okay, make sure you draw this first. Okay, you have this, your GMV pi. Okay, at R pi, voltage across R pi is V pi. Okay, here collector, you have also R naught. So this is fixed. Okay, so this is fixed. Okay, first thing you have to draw your hybrid pi model. Okay, so isn't it look similar? So you have R pi, GMV pi, R naught. Okay, and then you have emitter. Okay, now let's transform your circuit just now, your fixed bias circuit, into the AC equivalent circuit. Let's go point by point. All right, so let's take a look at the emitter first. Okay, emitter. So as you can see there, emitter is grounded. So just make a ground here. All right. Okay, and then we will go to the base. Okay, base. Okay, what do you see here? At base, you are seeing an RB go to the ground now. Okay, so at base, okay, the same node. So this is your base. Okay, we'll go to the RB and go to the ground. Where is ground? Ground is the same node as emitter because emitter now become grounded. Okay, emitter is grounded, right? So this is your RB. Okay, what else at base? So at base, so you have here straight to the V in. So you are actually having this point is your V in. Okay, so you've done for the input part from base to the emitter. Next is at your output part. Okay, let's take a look one by one. Okay, at your output part. As you can see, your DC analysis circuit, okay, you have your output part is VCE. Okay, VCE, a voltage here. So, but in AC analysis, it has been replaced by a current source GM V pi. Okay. All right, so let's take a look at the collector here. So collector here, what do you have here? So you have RC to ground now. Okay, so RC to the ground. So you have here RC. Okay, what else do you have? Nothing else. Okay, if you have more resistor, then you have to put all the resistor. But again, you have to go from node to node. Okay, so from collector also you have V out. So at this point, you have your V out. Right? So this is how you simplify the circuit. Okay, this is how you get the equivalent circuit. Okay, AC equivalent circuit. All right. So from this point, okay, you know that here you have your I in. Okay, I in. All right. So here at the base, you have your IB. All right. So, and also at the output, okay, you have your I out here. Okay, in this case, I in and I out are open. We have no resistor there. Doesn't matter. Okay. All right. So this is how they simplify the circuit. Do you have any question? Okay. Okay. Right. Before that, okay, since the analysis is include the Z in and Z out, okay, the AV, which is the voltage gain, the current gain, okay, so you have to put all the notation, okay. Here at very front of your circuit, okay, here as you can see, the arrow of Z in here, okay, starting from this point at V in, okay, so this is your Z in, so this is your Z in, input impedance. So Z out is from this point, okay, is equal to the Z out. So this is your Z out. Okay, so you have to put very clear all the parameter needed. Okay, so this is how you transform. Do you have any question before we derive other parameter? Or very clear? That's good. Okay. All right. So now, okay, after you simplify the equivalent circuit, there you go. Okay, the input impedance, the output impedance, the voltage gain, and also the current gain. Okay, I don't want you to memorize all this formula. Okay, but we do the derivation together. Okay, so basically you can derive it all. Okay, I'll go back to this slide. Okay, so for this one, okay, so you have your, okay, let's take a look the Z in first. Okay, Z in. Sorry, I need to uh move here. All right, so let's take a look the Z in. Okay, Z in. Zin is the total resistance or the total input impedance, means the total resistance that you see from this point, okay, from this Zin point. Okay, what are you seeing the resistor here? What are the total resistor there? Someone? So you are seeing what? RB. What else? R pi. Yes, correct. Okay, so what happened the two resistor? Because these two resistor is in parallel. Therefore, the Zin is you just parallel the RB parallel with R pi. Okay, that's how you get your Zin. Okay, so Z out. Okay, let's take a look the Z out. So what did you see from this point Z out? Okay, your eyes is at the arrow here. Okay, what are you seeing here? So the Z out is equal to RC parallel with R naught. Okay. All right. So we have got all the equation for the input impedance. All right. So now let's take a look on the voltage gain. Okay, voltage gain. Okay. So this voltage gain. All right, this voltage gain. Okay, let's take a look together on the voltage gain. So AVOC is equal to the V out over V in. Okay, let's write first the equation. Okay, so now you have AVOC, okay, is equal to, why AVOC? Why? Because you don't have resistor RL here at the output. Okay, in this case, okay, usually it will be a closed circuit, okay, where you have RL over here. But now it let be open. Okay, there is no load resistor here. Therefore, we use AVOC. Okay, voltage gain at open circuit. Okay, so we know that voltage gain is equal to the V out over V in. Okay, let's take a look together what is V out. Okay, so V out is equal to the IR, right? Okay, so V out is equal to the IR, means that V is equal to the IR. Okay, so what is current total at the output here? So current total at the output here is the current source that has been provided here. Okay, so but this one is in opposite direction to down. So V out here is okay, if I didn't draw like this, so I think you can imagine this, right? All right, doesn't matter, I cannot erase this, doesn't matter. All right, so the total current is actually GM V pi. All right, okay, but then, okay, since your voltage V out here, the top is positive, okay, you should get current that going down to the RC. Okay, so what is the R here? R here is actually the total resistor. Okay, total resistor RC parallel with R naught. So that's how you find it. But then we have one problem here, because the total resistor there, the current should be going down in order to get positive V out. Okay, therefore your current is now is upside down, going down. You should get current going up like this, okay, in order for you to get positive V out. Okay, so you have to put negative GM V pi, okay, in order to vice versa your current direction. Okay, so now V in. So let's take a look the V in. Okay, V in. So V in equal to what? Now, okay, as you can see here at the input part of your circuit, okay, that's why I said I have to put all the notation V in and V pi. As you can see that V in here is equal to the V pi. Okay, from this node base to the ground is V in. Okay, since this is in parallel, therefore V in is equal to the V pi. Okay, so you write down your V pi here. All right. Okay, so that's how you get your AVOC. Okay, so you can simplify by cancel out the V pi. Okay, now your AVOC will become negative GM times RC over, RC parallel R naught. So this is your AVOC. Okay, from the equation here, stated that AVOC is equal to negative GM times R naught parallel RC. So how this equation get, okay, in the textbook and this slide is from this derivation. Okay, you have to go one by one. What is V out and what is V in? And you have to cancel out the V pi. Finally, you have simplified the equation equal to negative GM RC parallel R naught, which is similar to this one. Okay. Okay, so let's take a look on the what else. Okay, what else? So current. So we have done the input impedance. Okay, the output impedance, the voltage gain down done. Okay, next is the current gain. Okay, the current gain. Okay, let's take a look on the current gain. So how this equation derive the current gain? So it is actually same like what we have done in here. That's why I put it here so that all of you can recall on your own. Okay. So for the current gain, so that's how you solve it. So you have the current source here. Okay. You have the current gain like this. So this is your current gain. Okay. So maybe you have forgotten, but we will be using the same circuit here. All right. So you have the AVOCV in, Z out, and RL. So let's take a look here for the current gain. All right. So your current gain is equal to AI is equal to I out over I in. Okay. So you will be using the same voltage model. Okay, like before. So you have this circuit, if you still remember. Okay, AVOC. So this is AVOC V in. Okay, this is the Z out. Okay, and this is your RL. Okay, so RL current going out here is I out. Okay, for this case, okay, so your I out is equal to the, so this loop, okay, so it has been simplified by using this, okay, so this loop, if you want to get your I out, it is equal to the AVOC V in, okay, over, let's write one by one first. Okay, so for this case, I out, oh, where should I write this? Okay, so I out is equal to the AVOC V in, okay, over Z out plus RL. It's like the KVL loop there, okay? Same thing. So now, what is V in? So I out is equal to the AVOC. Okay, what is V in? Okay, so V in is voltage across here, the V in. Okay, so V in is equal to the, can I say that V in is equal to the I in Z in? Okay, V in is equal to the IR, so it is equal to the I in Z in. Why I do that? Because I want to get I in equal to I out over I in, because I want to take to have, I have to create these two. Okay, I have to make these two visible. Okay, in order for me to get the formula. Okay, finally over Z out plus RL. Okay, so as you can see, you have I in at the right side. Okay, therefore, you can bring your I in to the left side. Okay, so you have, oh, so this is I cannot write it here. Okay, so I out over I in. Okay, you take out the I in from right side to the left side. So you will get here I out over I in is equal to the AVOC over, sorry, AVOC Z in over Z out plus RL. Okay, so that's how you get the the current gain. Oh, okay. Doesn't matter. So this is your current gain. Okay, so that's how you get the derivation for the current gain. So I have to write it here, OVOC V in one more time. Okay, so that's why they get the I in is equal to the AVOC Z in over Z out plus RL, where the AVOC, you already got the value, the equation here. Okay, negative GMV pi RC parallel R naught. Okay, you can replace those two, and finally you will get your AI is equal to the negative GM RC parallel with R naught. Okay, times Z in over Z out plus RL. Okay, that's how they derive it. Okay, in here, they don't have the RL. In this circuit, they don't have the RL. Usually, you're going to have RL here. Okay, we will take a look on the example. You're going to have an RL parallel with the RC here. Doesn't matter. I'll show it in the example. Okay, so do you have any question about this derivation? So basically, what has been written here, okay, the formula here is we already derive it here. Okay. Okay, we derive it all here. Okay, usually, okay, R naught is very, very big. Okay, so you can actually, if you parallel RC, parallel with R naught like mega, so you will get Z out is equivalent to the RC. Okay, but if you do straight away parallel these two, no problem. Okay, basically you will get like almost equal to the RC value. All right, so the amplifier step analysis. All right, so this is how you solve it. Okay, so we have solved it. Okay, so analyze the circuit DC point just now, and then blah blah blah. So the same thing. Okay. Okay, so this is the parameter. So first thing, so this is how we, so this is another common emitter. So common emitter for this one is quite straightforward. Okay, because you have fixed bias circuit, RB, RC, and emitter. So if you still remember this type of circuit, which is the voltage divider, so you have to simplify this circuit and get the what we call it, the AC analysis. Okay, so what you do with the capacitor will be shorted, and VCC will be grounded, and then this shorted and this one also shorted. Okay, so when this capacitor shorted, okay, for example, so C1 is shorted, C2 is shorted, now C3 is shorted. Okay, what happened to the RE?
Short.
Short circuit.
All right, it will be short circuit as well. Therefore, you can imagine that your hybrid pi model, the AC analysis emitter will go straight to the ground. Okay, will go straight to the ground. All right. So first step, okay, capacitor all shorted. All right. And then the symbol used for the current is in small signal analysis. Everything you have to put it. Finally, you will get the AC equivalent circuit like this. Okay. So that is how you do it. Okay. So I will derive the circuit. I mean, I will do the simplification of this circuit. Okay, by using this example. Okay. Okay. So for this first example, we will do it together, but I might expect you to do the example on your own. Okay. All right. Sorry. Got it. Okay. I have to add one more. Okay. Okay, so determine the values for Z in, Z out, AVOC, AV, AVS, I in, IS, blah, 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 and AP, okay, given VA equal to 200 volt. And in this question, given also the IC, okay. But in the test later, test 2, sorry, you will have to do the derivation all the way from the DC analysis to get the RC, okay, as well as the AC analysis. Okay, but this one I have to short the time. Okay, if you do the analysis of this circuit, you will get IC equal to the 2.37 milli. Okay, so let's do the first step together. Okay, okay. So for SC, for this one, okay, first thing is, can you see my circuit here? Okay, so this is will be short circuit, capacitor short circuit. Okay. Okay, all capacitor short circuit, okay, as you can see. And then VCC is also grounded. So this one will be grounded. Okay, VCC will be grounded. And then what you do next is, I say it, draw the hybrid pi model first. Okay, so if you draw your hybrid pi model, okay, like this. So I will draw it at the center. So you have this one, R pi. Okay. This is your base. Okay, don't forget R pi. You have V pi. Okay, what else? Okay, what else? You have your GM V pi and R naught. Okay, so you have your GM V pi here at collector. So this is your emitter, and at collector here you have R naught. Okay, so from base to emitter, okay, so first thing first, okay, since this capacitor C3 is shorted, okay, what happened to this RE? So this part shorted, since this is in parallel, therefore R3 also shorted. Okay, so we have no longer R3 in your AC analysis circuit. Okay, therefore emitter, so you have base, collector, emitter, and emitter will go straight to the ground. Okay, so this is just your hybrid pi model. Okay, let's start together from the base. Okay, let's see together from the base. So at the base here, okay, what do you have there? Okay, so at the base here, you have what? You have R2. You from base, you have R2 to ground. Okay, ground. So draw your R2 from base to ground. Okay, the same ground as emitter. So this is your R2. All right. Okay. At base also you have R1 to where? Now VCC has become grounded. Therefore R1 to ground also. Okay. At base also you have R1 to the ground. All right. So not finished yet your base because it has the input source there. Okay. Therefore at base, so this C1 has been shorted. You have RS. Okay, RS. And from RS, you have your VS to the ground. Okay, so this is your VS. Okay, so given all the value, okay, don't forget to put your V pi there, and there is also V in stated here. Okay, so you have to put your V in plus minus V in at this point, and also your Z in before RS. Okay, so this is your Z in. Okay, as you can see, ZIN is not included with RS because ZIN is after RS. I mean, starting from this VIN. Okay, if you don't want to get confused, you might have to draw your RS a little bit, go back there near the VS. Okay, so that's how you draw it. Okay, so this is the input part of your AC equivalent circuit. Okay, so this is your AC uh, equivalent circuit. Okay, so let's go to the back. Okay, your capacitor, sorry, your collector. Okay, at collector here, let's go together. So you have what there? You have from collector, you have RC to the ground. Okay, RC to the ground. Okay, and then you also have from this collector, sorry, so this capacitor short, and you have RL. Like I said, most of the amplifier circuit has output loop, load resistor, which is RL. Okay, at RL here, you have your V out, put all the notation. Okay, look at the Z out arrow. Z out arrow is before your RL. Okay, so Z out is not here, wrong. Okay, so Z out is V4 RL, which is equal to this portion. Okay, Z out is equal to the RL, like that. Okay. All right, so do you have any question? Student, this is very important. Do you have any question? No question. I may proceed.
No
Okay.
question.
Okay, great. Okay. Okay, so make sure you clear. Okay, so what has been derived here, like very so you can actually refer any proper drawing here, but then it is the same thing. Okay, here. Okay, what I have shown here. Okay, but we go from point to point. Okay, in the test later, test 2 later, you have to draw from point to point. Okay, from base to ground, from emitter to ground, and from collector to ground. Okay. All right. So before we derive the voltage gain, the current gain, let's take a look on the Z in. Okay, Z in is equal to what?
R1 parallel with R2 with R pi.
You hear me? Hello? Hello?
Yes, can do.
Oh, just now no one answering me. It's like I'm talking to myself. So Z in is equal to what?
R1 parallel with R2.
Hmm? Hmm? Again?
R1 parallel with R2 parallel with R pi.
Yes, correct. So don't forget your R pi there. Okay, so the total resistor that you see from this arrow. Okay, so you have R1, R2, and R pi all parallel. Okay, now Z out. That's why when you look at the question, you have to carefully see where is the arrow of your Z out. Okay, arrow of your Z out is before RL. Okay, therefore when you draw your AC equivalent circuit, Z out is before RL. Means that Z out does not include your RL. What is Z out represent to?
RC parallel to R0.
Correct. So RC parallel with R naught. Thank you. So R naught parallel R naught. RC parallel with R whatever. RC parallel with R naught. Like that. Okay. Okay. Okay, thank you, the two students. All right, so next one is now we have derived the Z in and Z out. So let's us derive the, like I said, you don't have to memorize because that's a lot of formula. This is just for common emitter. So you have common collector, common base letter. So you better understand this so that you don't have to memorize. You can derive, okay? All right, so let's take a look on the
Madam, do you speaking?
yeah,
I
yeah,
cannot hear
I'm
you.
disconnecting now. And can you hear me?
Now can.
Okay, okay. Sorry. Okay. All right. Okay, let's calculate the R1 parallel R2 parallel R pi. How much is it? Okay, so let's calculate for the R.
All right, can you hear me now? Hello?
Yes, yes.
All right, okay. So I will be using, I don't know what's the problem. Okay, it's okay. Okay, so let's straight away calculate it. Okay, so you have your RPI. Okay, so from the previous slide, okay, so RPI is equal to the beta over GM, but first you need to calculate your GM. Okay, GM is equal to the IC over VT and RPI equal to beta over GM. Okay, so let's calculate first the GM. Okay. So RPI is equal to the beta over GM. Okay. And GM is equal to the IC over BT. Okay. So this one, GM, you will get the value for GM is, can someone calculate for me the GM? So beta is 120. Can someone calculate GM for me? So I have calculated it actually. Okay. So oh no, I didn't calculate. Is it? Yeah. 91.15 milli. Milli. Therefore, RPI is equal to 1.32 kilo ohm. Okay. Now you can calculate your Z in. Okay. Z in is equal to the R1 is 8.2K. K parallel with R2 1.2K, sorry 1.5K parallel with R pi which is 1.32K. Finally, you will get your Z in about 647. Is it?
Doctor,
Mm-hmm.
what is the value of BT?
26 millivolt.
Okay. Thank you.
All right. So can someone parallel all these three resistor? 8.2K, 1.5K, 1.32K.
647 ohm.
647 ohm. Okay. Okay, now Z out. Okay. R0 is equal to the VA over IC. Okay, as you can see there. Okay, VA, I'm not sure in this question given VA value or not. So VA is given 200. Okay, therefore you can calculate your R0. Okay, so R0 is equal to the VA over IC. Okay, so VA over IC is actually you get 83.39K ohm. Okay, so RC is given as 4.3K parallel with 83.39K. You will get your Z out. I have calculated it. It is 4.09K. Okay, 4.09K ohm. Right? Okay, so that's it for the Z out. Okay, so now let's take a look on the AV. Okay, AV. All right, so the question asks AVOC first and then AV so long. Okay, but it's okay, we'll do it together. Okay, so you know that your AVOC is equal to the AVOC means, okay, AVOC means V out over V in without RL. Okay, without RL. So this is AVOC. Okay. Okay, because the question want the open circuit first and then the AV back. Okay, doesn't matter. Let's take a look. What is V out over V in without RL? So what is V out over here? What is V out? Okay, so you have V out is equal to the IV. Okay, so total resistor without RC, without RL is R0 parallel with RC. Okay, you know that this current time resistor. So resistor with the RL is R0 parallel with RC. So what is current over here? So total current is GMV pi, but now GMV pi is going down. Therefore, you should have your current negative GMV pi. Okay, negative GMV pi. Okay, so V in, okay, let's take a look here, V in. So V in here is equal to the V pi. Can I say V in equal to the V pi? Can, because all of them are in parallel. Okay, the reason is we want to cancel out this V pi. Okay, finally you cancel out the V pi, you will get the AVOC without RL is equal to GM parallel with RC. Okay, so that's how you got your AVOC. Okay, AVOC. All right, so now let's see for the so next question. Okay, so you have Z in, you have Z out, you have AVOC. Now you want AV. Okay, you want AV. Okay, so now AV must be okay, this one again, the voltage gain V out over V in must be with RL. Okay, must be with RL. Okay, therefore we will do a straightforward thing. Okay, a straightforward circuit. Okay, so V out over RL. So this one is equal to the IR. So R in this case with RL is equal to what, student? If we include V out, okay, V out, we include RL, so the total resistor is all these three resistor, okay, which is R0 parallel with RC parallel with RL. Okay, what will be the current? So the current is actually the same thing here, which is equal to the negative GMV pi, okay, because it is in the opposite direction, negative GMV pi. So what is V in over here? Okay, what is V in over here is equal to the V pi, same again, so you cancel out. So AV with RL is equal to the negative GM R0 parallel with RC parallel with RL. So can I say that it is equal to the negative GM Z out parallel with RL? Yes, you can. So you have actually derived all these two, AVOC and V out. So how to get the values? You have to put all the values that you have calculated just now for the GM and R0. Okay, RC you have. So I just put the number here because I have calculated it. It is actually negative 373. Okay, for the AV with RL, you got here about negative 265. Okay, later on you can calculate yourself. Okay, because we don't want to waste our time here. Okay, because understanding is more important. 265. Okay, negative 265. All right. So do you have any question for the Z in, Z out, AVOC and AV? Student? Student? Hello? Can you hear me? Am I disconnecting? Okay, great. Okay, so no question. All right. Okay, so yeah, we derive every time because I think it one student messaged me, do we have to derive every time? Yes. Okay, if you can memorize all things on your head, go ahead. But for me, it's better to derive. Okay, not difficult one. It's like KVL and also Ohm's law only. Okay. Okay. Next is AVS. Okay. AVS. Okay. If you still remember, AVS is equal to the V out over Vs. Okay. But then AVS has been shown in the last class. Okay. We make use of it. So V out over V in time V in over Vs. It's like you cancel out these two. Okay, so AV for so V out over V in here, you already have your AV. So now left with V in over Vs. Okay, so let's take a look on the circuit at the input loop there, student. Here. Okay, so you have here, okay, at the input loop here. So V in there, okay, is equal to what? Can we use voltage divider? No one responding. Okay, doesn't matter. Let's draw together. So this is your V in, this is your RS. So the resistor here is Z in, and this is your V in, this is RS. So how do you get V in, student, here? V in, someone please?
Voltage.
Yes, Z in plus, Z in plus. Z in over Z in plus RS times Vs. Okay, therefore V in over Vs is equal to the Z in over Z in plus Rs. Okay, so you have this portion now. Okay, you can put in the formula. Therefore, this formula, okay, will be the arrow here. Okay, so it is equal to the AV times V in over Vs is Z in over Z in plus Rs. Okay, so if you were to calculate this AVS, okay, plug in all the value because you all have all the values AV, Z in, Zi and Rs. So you will get about negative 137.5. Okay, you can calculate later again. Okay. Okay, now we have done for the AVS, okay, but we not yet finished for the AI and AIS. Too many, okay. But most importantly, you understand, okay? Okay, let's me put one again, the slide here. Okay, let's derive for the AI and AIS, okay? So for the AI, okay, you know that for the AI, AAI is equal to the I out over I in. All right. So what is I out and what is I in? Okay, so you know the from your equivalent circuit just now, you might see that okay, so I out here. Okay, this is your equivalent circuit. So where is your I out actually? So I out is where? Okay, so given the circuit like this, so where is your I out? So I out is going here. Okay, so if you put in your circuit here, so this is your I out. Okay, this is your I in. Okay, I out and I in is over there. Okay, so if you want to find what is I out, okay, I out is equal to the, what is I out? Someone?
V out for RL.
Yes, V out over RL. Okay, so there are two ways actually. So let's do the first way lah. Okay, so if you still remember, so this is since you have calculated your AVOC, let's do this way first. Okay, so you have your amplifier model. Okay, so we'll be using this. Okay, so this is your I out. Okay, from here, what is your I out from here? So there are two ways actually. So I out is equal to the AVOC V in over Z out plus RL. Do you agree with me? Yes. Okay. So this is
Yes.
amplifier model that because we already calculate the AVOC, so we make use this amplifier model because we already have the value for the AVOC. Okay. So now we haven't have the I in yet. Okay. So you write it again. Okay. So now V in is equal to what? V in. Okay, V in is equal to the, if we take a look here, can I say that V in is equal to the I in Z in? Can I
Yes.
say that? Yes. Okay. So it is equal to the I in Z in. Okay. Over Z out plus RL. Okay. You will get here. Now you have your I in equation here. Therefore, I out over I in, which is equal to the AI, current gain is equal to the AVOC over Z out plus RL. Okay, if you plug in all the value, AVOC, Z out, I left with Z in here. Yeah, thank you. So if you put all the value, you will get like negative 17.13. Okay, negative 17.13. So that's how you get the I out and Z out. Okay, do you have any question before I move forward? No question. Okay, all right. Okay, so now the question one, AIS. Okay, AIS. Okay, current gain referring to the source. Okay, AIS. So AIS is equal to the I out over IS. Okay, you actually can do this I out over I in times I in over IS. All right. So from the input loop just now, okay, you have VS, RS, and R in. This thing, so you have this, okay. So you actually can transform this circuit, okay. You can transform this circuit become a current source, okay. So you have like this. So this is your IS. Say instead of VS, you have in series with your RS. So VS series with RS. Now you have IS parallel with RS. So you do voltage to current transformation. Okay, and then you have Z in. Okay, this is your Z in, and this is your I in. This is your V in. Okay, therefore from here you get that. Okay, so I in, if you use current divider rule, okay, current divider rule, you will get your I in is equal to what? Current divider rule, student?
RS over RS
Correct.
plus Z in
Correct. Okay, RS plus
time IS.
yes times IS. Okay, just now we do voltage divider rule. Okay, so this is VDR. Okay, this time we do CDR, current divider rule. Okay, so now you have the portion of IS, I in over IS is equal to the RS over RS plus Z in. Okay. Okay. So finally, you will get your AVS is equal to the I out just now, which is this portion is equal to the AI. Okay, times RS over RS plus Z in. Okay, plus Z in here. So you will get your AIS. Okay, sorry, I have to write it properly. So AIS is equal to the negative 8. Negative 8.24. Okay, negative 8.24. All right. Okay. Okay. So finally, they want AP. So AP is equal to the AV times AI. Okay. So you multiply these two, you will get like about 4.54K. So all the voltage gain, okay, doesn't have unit. Okay, why voltage gain, current gain doesn't have unit? Because you cancel out the unit. Okay, V in over V out and so on. Okay, you cancel out the unit. So no unit. All right. All right. So do you have any question? Do you have any question? So let me take a look on the chat box now. So what? My brain is evaporated. I'm having brain cramp. Doctor, are you talking now? Yes, I'm talking right now. Okay. Evaporated, say with me. I'm lost. I'm a lost boy from Netherlands. Netherlands or Neverland? Oh my God. I'm trying to explain a very detailed. You said that you're lost? Seriously?
Doctor, we are barely keeping up.
What?
We are barely keeping up.
Oh, okay. All right. Okay. So, but yeah, it is quite a lot of derivation, okay, student. So basically, you can actually memorize, okay. But do you think you can memorize all? Okay.
Definitely cannot.
Yeah, definitely cannot. That's why I am trying to make you understand by deriving from the circuit to the formula one by one. Okay, so you might be lost now, but you will thank me later. You are welcome. Let me say you are welcome now. Okay, so you will thank me later because this concept will be using in the common collector and also common base. So this is just the beginning of your life. No. So this is just the beginning of this AC analysis circuit, okay, with the common emitter, okay? Okay, so don't lose, okay? I'm here with you, okay? I'm trying my best to explain, okay? I hope that you all appreciate my explanation here because I go through one by one, okay? All right. Let's take 5. Maybe we should have take 5. Okay. Okay, let's take 5. Let's take 5. Okay. Take 5, everyone. You will thank me later, seriously. Okay, take 5, doesn't matter, okay? We go slowly.
Madam,
Done?
can I ask a question?
Yes.
The VT is constant 26 milliwatt.
Yes, correct.
Okay.
For all the time. Hello? Can you hear me?
Yeah, yes, I get.
All right. Yes. Okay. So VT is constant, 26 millivolt for all the time.
Yeah.
Okay. So as you can see, oh no, you cannot see because I didn't show it yet. Okay, as you can see in the textbooks, like, yeah, they put all the answer like straightforward like this. Okay, but then where do you get this value? So actually from what I have written and derived with you together just now. Okay, you can memorize all, but then I won't advise you memorize. Okay, so go back to all this derivation. Okay, and then do on your own. Okay, so leave this exercise, okay, for all of you. Okay, so I want you to do, each of you has to do it this one, and not individual, not grouping, but individually. Can you please submit to the Padlet? Okay, to the Padlet. Okay, so you submit in your column group, but for example, group 1 has 3 students, so I want to see 3 answers there. Okay, can you do that? So it is a good exercise. Okay, so why this is not a punishment or what, but you will thank me later. Okay, so try to do this exercise. This is exactly the same like this example, but then values are different. Okay, so what you should do, I want you to derive, okay, everything here. It's like you replicating what I did here, okay, but this exercise, okay. So the deadline is, doesn't matter as long as before our next class, okay. Okay, so there you go. So the next part of it, okay, so common emitter. Okay, so for the common emitter, so previously, okay, we have no RE. Okay, it is a bypass RE because we have collector, we have capacitor in parallel with the resistor. Then this capacitor short, so RE short. Okay, this time, you don't have capacitor here. Okay, you don't have capacitor here. Where you have to include your resistor RE in your AC equivalent circuit. Okay, so let's derive together. So this is still common emitter. I think I plan to do common emitter only today. Okay. Okay, like I said, so the textbook and also the slide has derived it for as listed out the equation, but then let us derive together. Okay. Okay, so this is your circuit. Okay, so first thing is to okay, so the capacitor here, you short circuit, don't forget, and then the voltage source here grounded. All right. Okay, so here you have to draw your hybrid pi model. Okay, again and again draw your hybrid pi model. So you have your hybrid pi model is you have R pi. Okay, R pi from base, and then R pi from base to emitter. Okay, and then from collector to emitter, you have GMV pi. Okay, and then what else you have? You have V pi here. Okay, now let's take a look one by one from base. Okay, let's take a look on the emitter first. So emitter, what do you have here? Okay, since you don't have capacitor here, so you don't have shorted capacitor there, therefore you have to include your RE in your AC equivalent circuit. Okay, so meaning that at the point of emitter here, you have RE to the ground. Okay, RE to the ground. So you have your RE here. Okay, see, your circuit become more bigger and complicated. Okay, doesn't matter. Okay, so next is your base. Okay, base. What do you have here? So you have base. Okay, I think too panjang here. I make it short. Okay, at base you have resistor RB to the ground. Okay, resistor RB to the ground. So you have RB here. okay, to the ground. So this is your RB. Okay, and then you have your V in plus minus Z. So this is your V in. Okay, where does your arrow of V in? So before RB, so therefore this is your Z in. Okay, so where is the collector? So at collector here, what do you have here? You just have RC here. Okay, RC. And then what else from this collector? You have short circuit C2 and V out. So you have here V out. Okay, so that's how you draw your AC equivalent circuit. Okay, do not forget your Z out, you're seeing from here. Okay, so this is your Z out. Okay, okay, so that's it for the AC equivalent circuit. Okay, now we want to derive for the Z in. Okay, Z in. Okay, previously, student, you have like quite straightforward. Okay, you have Z in like this, so you don't have RE. Okay, it's like you can see that from Z in, from that moment, from that point of Z in, you can see that R1, R2, and R pi is all in parallel. But then in here, you have your RE. So the circuit has become a little bit complicated here. Okay, a little bit lah, not many. Okay, a little bit complicated here. Okay, so so you cannot say that RB is parallel with R pi plus with RE. Cannot, because these R pi and RE are not in series. Why? R pi is at base to emitter, but then RE is emitter to the ground. So it is not in series actually, not in series. It might look series, but it not in series. Okay, so there you go. It comes with the new parameter. We call it as Z in B. Okay, Z in from the base. Okay, Z in from the base to the ground. Okay, as you can see the derivation here. So we have Z in B. Okay, ZB or Z in B. Okay, how do this textbook get this value? So this is how the derivation. Okay, so from here, so let's take a look here. So we have Z in. We might say that this Z in is, this is your, okay, so this is your IB. Okay, so this is your, let's say we have said this is a V in or V total. Okay, so V in and V total are the same. Okay, so let's take a look here. So from this point to the ground, actually we have your VE. Okay, if you still remember. Okay, so V total actually is equal to the V pi plus VE. Okay, all right, V pi is equal to the IB because it at base. Okay, you have current IB here flowing to the R pi, IB R pi. Okay, but at VE here, you have IE RE. Okay, IE RE. Okay, but do you still remember that IE is equal to the student? In terms of IB, can someone say IE in terms of IB equal to what? Beta plus 1 IB RE. Still remember this? Beta plus 1 IB? Yes,
Yes.
okay. All right, great, student. All right. So this is VT. Okay, this is VT. Okay, now I want to take this VT. Okay, so your VT here. All right. Okay, so VT here is equal, so Z in B, we might say, okay, Z in B is equal to the V total here. Okay, from this node you have V total. Okay, V total over current in, which is IB. Okay, so Z in B is equal to the VT over IB. Okay, if you take out these both IB to down, okay, the equation will be left with R pi plus beta plus 1 RE. Okay, so this your equation will be like that. Okay, so Z in B is equal to the R pi plus beta plus 1 RE. Okay, that's what has been written in the textbook here. ZB or Z in B, the same thing. Okay, R pi plus beta plus 1 RE. So this is how they derive it. Okay, this is how they derive it. Okay, so finally your Z in. So finally, your Z in is equal to the RB parallel with Z in B. Okay, so it is equal to the RB parallel with R pi plus beta plus 1 RE. So this is how they derive the equation. Okay, so okay. Do you have any question, student? Hello? Everyone clear?
Yes, ma'am.
All right, great. Okay, thank you. Okay, so next one. Okay, so next one is the, I can say the tough part. Okay, so I put the tough part later. Okay, so as you can see, Z out is actually, you cannot take like it is equal to the RC. Okay, there is a derivation behind it. Okay, actually after the derivation, I will show you the derivation, but finally after the derivation, Z out is actually equivalent to the RC. Okay, let's take a look on the derivation of Z out. Before I derive the Z out, which is much more complicated, so I think I will derive the voltage gain first. Okay, let's derive the voltage gain first. Okay, so for the voltage gain, okay, for this one, so you have your AV. Okay, in this case, your circuit, you don't have RL. Therefore, this is AV open circuit. Okay, which is equal to the V out over V in. Let's take a look together. Okay, let's take a look together. So V out here, okay, as you can see, V out is equal to the voltage across RC. Do you agree with me? Yes.
Yes.
All right. So the current is actually same like in the common emitter previously. We take the total current source with each GM V pi. Okay. So it is actually equal to the GM V pi times RC. But then GM V pi is going down, but your plus voltage here is on top. Okay, it must be current going down like this, okay, in order to get plus V out. Therefore, your current here is negative GM V pi. Okay, one more thing is, what is your V in? Okay, let's take a look here, your V in. So you have your V in over here. So this is your V in over here. Okay, so it is actually equal to what, students? So it is actually equal to the V total. Do you agree with me? Yes, so it is actually equal to the V pi plus VE. Okay, this portion, okay, this portion, okay, V pi plus VE, which is equal to the this one, IB, blah, blah, blah. This one lah, basically this one, IB R pi plus beta plus 1 IB RE. So this is the V in. Okay, so let's write again here V in. So V in here is equal to the, okay, V in is equal to the V total, which is equal to the IBR pi, okay, plus beta plus 1 IB, okay, RE. Okay, That's how you get it. Okay, so now it's all the matter of cancelling out. I mean, you simplify your equation. Okay, so let's take a look on the V pi. Okay, V pi is equal to what? I have written it here. So V pi is equal to the IBR pi. Okay, IBR pi. So let's put IBR pi here. Okay, and then you have RC, and then you take out IV at the bottom here. So you will have R pi plus beta plus 1, RE. You close the bracket, so you will get, can you cancel out this IB? Of course, you cancel out this IB, you will get the simplification. Finally, it is equal, sorry. Okay, so it is equal to the R pi RC over R pi plus beta plus 1 RE. Alright, okay. So now, all of you okay? Still okay with it?
Okay.
Great. Okay, so I want to cancel out this R pi. So I divide all with R pi. So finally, because I want to get this equation, so finally they don't have R pi in here. So before that, they have R pi. Okay, now they don't have R pi. Okay, how they do it? Actually, they divide all with R pi. So they will get here negative GM RC. Okay, so they divide all with R pi. Okay, divide with R pi. Finally, they will get this equal to 1 plus GM RE. Okay, so finally, the AVOC is equal to this equation. Okay, same like in here, summer. Okay, so finally, we managed to derive it. Okay. Okay, so, no. Actually, they replace this R pi with beta over GM. Okay, so they replace R pi with beta over GM. Okay, so finally they cancel out the beta over GM. They will get that AVOC negative GM RC over 1 plus GM RE. Okay, if you still not believe in me, so you can do it yourself later. Okay. Okay, so do you have any problem regarding this? So it's like this actually. So let me need to show you. Okay, so it is actually negative GM. Okay, now R pi is equal to the beta over GM. Okay, and then RC, okay, over beta over GM. Okay, and then plus beta plus 1 RE. Okay, so that's why finally they get AVOC negative GM RC over 1 plus GM RE. Okay, you can try to derive on your own. Okay, but then I have put it here so you cancel out at GM, so you will get that portion AVOC. All right, do you have any question? I hope all of you still there. Okay, doesn't matter if it is online or face-to-face class, you will be facing this. Okay, so same thing here. Okay, so this is just the derivation for the AVOC. So let's derive for the I in. Okay, so this is the best part. Okay, for the I in. Okay, so sorry, not I in. So for the current gain, which is I out over I in. Okay, so I out over I in. Okay, so let's take a look on, since we have AVOC. Okay, therefore, if you still remember, you have your circuit here. okay, AVOC, V in, okay, and then you have here your Z out, and then you have here your RL, okay. So this is your I out. Okay, so let's take a look here. So what is your I out? Okay, I out is equal to the AVOC V in over Z out plus RL. Okay, but this one you don't have RL, but most of the circuit you have RL. So from here, V in we have derived previously, AVOC equal to I in Z in. Okay, so this is V in. So this one equal to Z out plus RL. Okay, and then this is your I out. So I out over I in. Okay, from right you take out to the left. So you will get that AVOC is equal to the Z in over Z out plus RL. So that's how you derive your I in. Okay, same like in the common emitter previously. Okay, so that's it. Okay, for the I out and I in. Okay, for example, what happen if they want you to derive the AIS? Okay, so instead of the voltage here, so you have the current gain here, IS. Okay, instead of you have series, you use voltage to current transformation. So here you have RS and here you have your Z in. Okay, and this is your V in. Okay, this is your I in. Okay, so I in is equal to the CDR, okay, current divider rule. So you have RS, okay, over RS plus Z in. Okay, and then you have IS here. So I in over IS is equal to the RS over RS plus Z in. Therefore, AIS is equal to the I in over I out. I write this so many times for you so that you can remember. Okay, so I in IS is equal to the RS over RS plus Z in. Okay, so that's how you derive your IS. All right, student. Okay, so that's it. Okay, so this is quite a long, very long because this is unbypass. Okay, unbypass RE. Okay, and you cannot bypass your RE. Okay, because there is no capacitor at RE, but then you have to include your RE in your circuit. Okay, so this is your RE in your circuit. Okay, so you have to include your RE. Okay, and then after that we derive also, okay, for everything here. For example, you have Z in B. Okay, Z in B is equal to the V total from base to the ground. Okay, V total from base to the ground is V pi plus this node is emitter, therefore equal to VE. Okay, V pi is IBR pi. VE is IERE, and you know that IE is equal to the beta plus 1 IB equal to RE. Okay, since we know that Z in B is equal to the V total over IB, because Z in B is total impedance from base to the ground, therefore you have to divide the current base, VT over IB. You cancel out everything, you got your Z in B to this portion, R pi plus beta plus 1 RE. And Z in is actually RB parallel with Z in B that you have derived here. That's why you have gotten this equation. Okay, and then we derive the AVOC, V out over V in. I think you have very much clear on this. So V out is the voltage across RC because we don't have RL here. Okay, voltage across RC is current total here is negative GMV pi time RC. Okay. And then V in here, you know from this particular node, V in is the same node as the V total from base to the ground. Therefore, we make use the formula that we have derived it here. So it is equal to the VT, IV, R pi, blah, blah, blah. And then you divide this. Okay, why they simplify it? R pi, we know that equal to the beta over GM. Finally, you will get this. Okay, you replace R pi equal to the beta of BGM. Finally, they get this. Okay, so it is actually the same thing here. Okay, but they didn't derive it for you here. I derive it for you here for your very much understanding. Okay, so don't forget your voltage divider amplifier circuit model. So it is look like this. This is at the input. This is at the output. I current gain equal to I out over I in. So you make use of the AVOC that you have derived before. So you get this one. Okay, so AVOC is I out over I out over I in is equal to AVOC this one. If they ask you to find AIS, then you have to derive this part. All right, student, are you still there? Are you there?
Yes. Yes.
Are you still alive, student? Can you breathe now?
Yes. No.
Okay, you may take a deep breath like me. Take a deep breath. Okay, I hope you can look back. I will upload this slide, definitely. Look it back and I'll try to understand it. Okay, all right. Okay, so my soul is flying away. No, come back, don't go away. Come back to where you belong. Okay, all right. Come on, student. I try my best to explain it to you. I hope you appreciate my explanation here.
We'll try our best to do.
All right, great. Okay. I know, take your time, but in order to understand, of course, student has to do revision on their own. Okay. Okay. Don't forget the exercise 1. Okay, you do it yourself and submit in the Padlet. Okay.
Okay.
All right. Okay, student. So I think I will end the class now. Okay. I'm afraid that that you might die if you continue this. No, no. No, just kidding. Okay. All right. Any question before we end our class? Hey. Oh my God, seriously. Oh, you all fall asleep already?
Any question? Let
Okay.
me refer back the slide first.
All right. I will upload the slide. Please, okay, please. I hope you do appreciate the explanation and please take a look again on the slide and the derivation again. But at least I have explained to you. You just have to recall yourself. Okay?
Okay.
Okay.
Okay. Can I get thumbs up from all of you? All right.
Okay, thumbs up.
Okay. Wow. Okay. All right. Okay, all. Please take care. Okay. Okay. Bye, all. Take care, all. Take a deep breath. Okay. Bye.
Bye.
Thank you, Doctor.
Okay. Okay. Take care, all.
Thank you
Okay.
very
Thank you,
much,
Doctor.
Doctor.
Welcome.
Uh,
Okay.
Doctor,
Yes.
can you share please the QR code? I couldn't scan.
Okay. Sure. Can you see? No?
Ah, yes. Thank you.
All right. Okay. Bye, all.
Okay, thank you, Doctor.
All right. Welcome. Bye, all.
Doctor, I haven't scan. Sorry.
Oh, okay. All right. I'll show you one more time.
All right.
Okay.
Thank you, Doctor.
Welcome. Okay.
Star.
Can you see the attendance?
Yes.
All
Okay,
right.
already.
Okay.
Thank you.
All right. Okay. Welcome. Bye, all.
Bye.